You can't talk about hydraulic problems without talking about contamination. This is it. This is the big one. So what is it? 80% of all failures are due to poor fluid condition. Um, Interpret that to mean there's crap in the fluid. Any material that's harmful on the fluid performance. And this is almost anything. It could be water, liquid, gas, solid, anything, anything. I just worked on a problem where they had a lot of rust in the hydraulics. Too much water in the system. So where does it come from? First of all, it could be building. I worked in a hydraulic factory for a little while, and it's amazing how dirty the hydraulics are when they're built. They don't meet our own specification of cleanliness that we expect of the customers. And if you get hydraulic repaired, it's even worse. They don't do anything to clean it. They'll replace the seals or whatever, but they don't clean it. So it's there, and it stays there because it's a sealed system. It could get sucked in somehow, and a lot of times, just because you got moving parts, it'll generate contamination. So what is building contamination? Well, it's stuff that you find in a machine shop, right? Birds, jets, flash splatter, dirt, dust, sand, moisture, paint, fibers, etc. It's invisible. You're not going to be able to see everything. In fact, just connecting a 5/8-inch hose creates 60,000 particles bigger than 5 microns. A micron, by the way, is 1/1,000,000th of a meter. And it could be dormant, just laying there waiting to break loose and make problems. So what is ingress contamination? Well, if you ever change the oil on your car, right, when you take off the cap, a lot of the junk and crap around the top of it will fall in. That's ingress contamination. So where does it come from in hydraulic systems? Well, it could be at the factory, it could be at the refinery, it could be at a storage unit, or it just sits there and stuff falls out of the air during transport, sitting in a barrel, especially the cap's undone. Again, even in the own reservoir, right? It's got those breather caps. They're not perfect. You're sucking in dirt. Again, here's some sources, right? Um, you got the filled cap. You take that off, just like on your car. Stuff's going to fall in. New oil is probably the dirtiest oil you ever get. It looks nice and clean, but there's crap floating around in it. That's why you shouldn't change your car oil um, much sooner than the factory spec, because what you're doing then is you're putting dirt in it with the new oil. Cylinder rod ends, dirt will stick to the rod and get pulled into it. And again, anytime you send it out for repair, they're going to get dirt in it. So generated contamination. This is where you get some kind of kinetic energy, and what happens then? It starts things start falling apart. It's kind of like watching sandpaper, right? All that sand just kind of disappears, right? So there's abrasion, erosion, adhesion, fatigue. We'll talk about cavitation later. Corrosion, rust, right? Or aeration, right? Bubbles are a form of contamination. This is abrasion, right? Different types. You just basically, it's like you have a particle hits a solid surface. It's like a bullet hitting it. It's just puts a little chip in it. Two body, you get a piece of dirt and moving bodies and just rolls around in there. If you ever seen a used hydraulic valve or any part was moving, you can see little scour marks on it. That's what this is. And then you got the type where it just rolls in there. And again, this will make a scour mark. So there's different types of abrasion. None of them are good. The next one I'm going to talk about is the fatigue. If you ever had like a paper clip, right, and start bending it, boom, boom, back and forth, it gets a little bit hot, gets weaker, 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 until finally it breaks apart. That's what happens on surface fatigue, is you get that little crack, that micro crack, and that thing will propagate like a windshield in the old cars. And what they'll do is they'll bend back and forth, and eventually it'll just break off. That's surface fatigue, just like breaking a paper clip. This is cavitation. This is how ultrasonic cleaners work too. If you take a bubble and it bumps into a surface, what happens then? It creates a little shock wave. That shock wave will travel around the surface of the bubble, meet in the middle at the top, and that will force the bubble to come down. It'll collapse on it. That surface of the bubble that's got a surface tension on it. Well, that'll slap that surface. It'll do it at the speed of sound. So it's just really flying. And you can tell when you had cavitation. If you ever open up a hydraulic component, it'll look like orange peel. That's a result of cavitation. It's a supersonic bubble hitting the surface and knocking it loose. Doesn't sound like much, but this is a lot of energy being hit in a small area. This is what happens for pump cavitation, right? You get some kind of restriction or even that elbow. We talked about this in the class. You increase velocity, pressure goes down, bubbles pop out, and then it gets pushed into the pump. And then if you look at that fitting, if you use the wrong fitting, like a pipe union or something like that, air can get sucked into there too. Get these bubbles. Well, those bubbles will get into the system, and cavitation, just like cavitation before, those bubbles will hit supersonically and cause a lot of damage. Again, this is what I mean by aeration. You got that union fitting or some kind of bad fitting, and air gets pulled into the fluid through the fitting. We used to do, when I was in the military, we used to do spectrographs of the oil, especially on our helicopters. And what we'd find is we knew exactly what was failing. Something's going to fail by looking at the metal that's in it. In fact, we used to put in marker metals. So, you know, one of the scariest things I ever heard is they came on the radio and said, land immediately. Your third planetary gear is going out. They did that through a spectrograph with marker, and they found the right mineral. And they knew that that was going to fail. But these are all the metals, right, and where they can come from. And we talked about premium gas too, iron being the source of octane. We said 80% in the previous slide. MIT says it's about 70%, right? And that's just surface degradation. But, you know, another 70 to 80%. By far, the vast majority of problems come from contamination. These are some tolerances that manufacturers typically use on their product. When we were making valves, we had plus or minus a couple 50 millions. 50 millions, I mean, that's how tight they are. So a little bit of dirt goes a long ways in the hydraulic system. So size matters. Ironically, the ones that used to give us the most problem are little silt particles because they can get into places that others can't, right? The other ones, big particles get stuck somewhere. Those are the easy ones. It's the silt particles. This is like getting your foot stuck in the mud, right? It just can't break free. So again, what's a micron? 1/1,000,000th of a meter. A good comparison is a human hair. It's about 74 microns, right? Interesting one here is bacteria, 2 microns. If you were to take a virus, it's 1,000th of that size. So these are really, really small, but they still count. All right, let's talk a little bit about pumps. This is a vane pump, right? So you got a couple things going on. First of all, you got the vane rubbing against the casting, and then you got the vane has to slide up and down in the little slots. Contamination will stop those processes. Okay, gear pumps, those intermeshing of the teeth, they're actually designed to have a little bit of hydraulic fluid, so it's never metal-to-metal contact unless you got some contamination in there. And the contamination will just eat up that clearance and take away that advantage of the hydraulic film between the teeth. Okay, this is a piston pump. That little piston and swash plate will rotate. And what will happen is it moves back and forth, right? So you got it in the cylinder blocks, you got the piston, and you got the swash plate. And these are the high pressure pumps. The higher the pressure, the more contamination becomes an issue. So piston pumps are the big ones. We talked about Bernoulli forces earlier. So was this valve. This is again the valve shifting. As it goes through those little cracks, right? What happens then is little particles will come in there, and they're just flying. I mean, and they'll hit on those seats. And what will happen then is they'll actually just take little chips out of it and round off those corners. And also, you got the balancing grooves. If contamination gets in there, your valve's going to stick. So a lot of can go wrong in a valve. This is a picture of what we're talking about with contamination uh, getting between the valve and the casting housing. And you can see either one, the small ones or the big ones, will be a problem. And eventually it'll bind that up, make that so that spool won't move back and forth. This is what we mean by those particles. Again, that velocity between the spool and the housing is just flying through there. So you get little particles. They're like bullets, and they'll just chip away at those corners. So you lose that sharp edge. So you get leakage. You get loss of performance. Uh, this is what we mean by erosion, high velocity erosion. It occurs right there. If any of you have aspirations for being an engineer and designing hydraulic valves, talk to me. But there's the spool on the left is much better than the spool on the right. I'll leave that up to you to figure out why. If you're working now and your company doesn't do hydraulic oil samples, do your best to convince them that you start needing to do this. Um, easiest way to check for contamination in your system is just look at the hydraulic oil. And I'll show you an example in the next slide. They actually have a technology where they can shine a laser through hydraulic oil, and they can count the number of particles in it, right? And then they come up with a specification about, all right, what are those particles? How much do I have? It's very easy to do, actually. It's amazing how simple it is. But this will tell you a lot. So back when I worked in hydraulics, we'd get parts back or components back from customers. First thing we'd do is check their cleanliness level. So we take a little bit of the oil out of whatever it is they sent back, and we count the particles in it and classify them by size. So ISO has a standard, a way of classifying this. In this case, we got 18, 16, 13. What that means that a particle size of about 2 micrometers, right? If you got an 18, that means you can have anywhere from 1,300 to 2,500 of those particles in a milliliter, which isn't much, right? It's a lot of particles. 5 micrometers, if you got 320 up to 630, you get a 16. And if you get the big particles, 15 micrometers, and you got somewhere between 40 and 80, you got a score of 13, right? The lower the numbers, the better, right? And if you get a new part, this will be in the instructions, how clean your system has to be if you want to keep your warranty. It's in there. Check it out if you ever see a hydraulic component. This is just the chart, how they code it. Again, ISO. This is pretty much an industry standard. And you can see if you got the number of particles, it will tell you what score you'll get. I'll talk about filters in a separate presentation. Um, but yes, you want filters. Uh, this will do more to extend the life of your hydraulic system than anything else. Yes.